Okay, so now we're going to finish up discussing Frank Kamenetsky theory today. And recall that Frank Kamenetsky initiation analysis was sort of correcting for Semenov theory by accounting for the fact that the temperature gradient in the energetic material prior to it exploding is actually going to have a temperature profile that is induced by the fact that the thermal conductivity of an energetic material is not infinite. And so that is, if you are generating heat at all points inside of the surface, you would expect from a basic heat conduction point of view, like for this 1D planar slab, where we have a uniform heating source term, and the temperature at the peak will be at the very center, basically just due to the heat generation. And the same argument applies to an energetic material. And so what we did then is basically, rather than starting from a control volume, we started from the full temperature form of the energy equation. We made a whole litany of assumptions here that it's essentially constant pressure and constant volume. And of course, that's only possible if you have an incompressible solid. And we assume that Cp is approximately equal to Cv. And also we assumed we're only examining ignition. So the mass fraction of the reactants is essentially 1 for the entirety of the process that we care about. Okay, and so then we work with the energy equation, crossed out all the terms that we don't need, and then we wound up with the sort of master equation here, which is just a heat conduction equation, but it is nonlinear due to this source term right here. We have a chemical reaction heating source term, and it is extremely nonlinear due to this Arrhenius term here. Okay, and it's extremely nonlinear due to both the exponential and the fact that the argument of the exponential is inversely proportional to temperature. And so that makes things, it's a sort of, as I said last time, it's a sort of nonlinear double whammy. Okay, and so, and then for this class, we'll just basically use the one-dimensional spatial operator, which you can then argue that for spheres or cylinders or slabs, it's equal to this, where x is the radial coordinate and kappa is a coordinate system selector. If kappa is 0, it's planar, and if it's a radial system, if kappa is either 1 or 2. Okay. Okay, so we basically go through this. We basically went through the boundary conditions. The classic Frank Kamenetsky assumed isothermal wall conditions. But also the Frank Kamenetsky equation is routinely solved using basically using a convective Robin type of boundary condition. Okay, and the classic initial conditions are that you started off at the ambient temperature, but you can generalize this, that you can basically have the outer boundaries fixed at some temperature T, and the initial conditions inside of it at some other temperature. Like for example, something I asked you to do on your homework is to emulate a case where you have the energetic at, say, 300 Kelvin, and I can't remember what temperature I used, it might have been 700, and then this energetic is subjected to a fire of some sort, and the wall boundary conditions are suddenly bumped up to 700 Kelvin. Okay, and so you could use Frank Kamenetsky to study what happens in this case here and examine how it ignites. Okay, in general, if you want to solve the full, the transient version of this equation, it has to be done analytically. And so I then worked a little bit further and showed that Frank Kamenetsky didn't have a computer, But he did argue that because we are interested in ignition, that the change in temperature prior to ignition is going to be quite small compared to the initial temperature. It's going to be at most, 20-ish Kelvin, and then basically that's a very small fraction of the initial temperature. So then what he did was he noted that the prime nonlinearity is with the inverse temperature in the Arrhenius term, and he just wrote that in terms of our small parameter q, and then he expanded this 1 over 1 plus q in the Taylor series to get this, and q is small, but it's not 0, so he just takes the first two terms. Okay, and so what he did with those was he then took the Arrhenius term and basically just rewrote it as EA over RU T naught times 1 minus T minus T naught over T naught. And that just gives you, and this is basically that's basically this Taylor series here with Q, with the definition of Q substituted in. Okay, and then we can separate this out. Then for the Arrhenius term, we can exponentiate it after we take the negative of this, and we wind up with this. It actually looks like more of a mess because we now have two exponential terms to worry about, but it's actually easier to work with because this exponential term here, that's just a constant. And this exponential term has temperature in the numerator, and that is much, much, much easier to work with. Okay, and so that is much, much easier to work with. And so Frank Kamenetsky did the Taylor series to get the Arrhenius term into this approximate form here, which then this form allowed him to use and to develop analytical solutions. Okay, and so that's sort of where I left off. And again, I am going to emphasize that Frank Kamenetsky is only interested in the initiation of explosions. He doesn't care what happens after that. So his model, especially with this approximation here, his model after it ignites is completely wrong, and he knows that, and he's okay with that. Okay, and so he's just using this equation to examine conditions on where thermally induced explosions can basically can occur. And like Semenov, he noted that these explosions will not occur if the heat generated by the chemical reaction is balanced by heat loss through basically through the outer boundary. So he analyzed steady solutions, okay, and he basically analyzed conditions where a steady solution is possible and a steady solution is not possible. Okay, and so that is much like Semenov, only there's a much more complicated equation to solve. Okay, and so in doing this, we can work with the steady Frank Kamenetsky equation, and this is the approximate form. And here we've just basically set partial t is equal to 0 because we just want the steady solution. Okay, and so we can solve this equation here if we are working with some sort of rectangular sort of prism-shaped energetic material, or if we are in 1D where it's a planar slab, cylinder, or sphere, or I should say infinite cylinder, or sphere, then we have this equation here that you can solve, and this is the one that we are going to work with, but it's still not really quite solvable yet. So one thing we're going to note is that I'm going to multiply both sides by basically rho Cp to get the thermal conductivity by itself. And I have Q rho here. And then I'm going to call this really dimensionless temperature here theta. Okay, and then what Frank Kamenetsky realized is that this theta here is an important parameter for ignition. So he used this dimensionless temperature here, which just came as a result of his Taylor series. He used this as a dimensionless temperature to define his system. Okay, and then he also he's a theoretician, so they like non-dimensionalizing things. And he also non-dimensionalized the radial coordinate and called it z. And z is just defined as the ratio of x over the outer boundary. So we have our sphere, and x is pointing from the center, and r naught is, that's a bad r naught, and r naught is the outer radius. Okay, so then we can use these two definitions and stuff them back into the governing equation here, and to basically non-dimensionalize it. Okay, and so we have, using the definition of theta, we have T is equal to T naught plus theta RU T naught squared over EA, and X is Z over rho naught. Then you can differentiate both of these expressions, and noting that T naught, RU, and EA are all constants. And so we have that dt is equal to RU T naught squared over E naught d theta, and dx is equal to R naught dz. Okay, and then we can basically use these definitions and show that dt dx is equal to this expression here, and d squared t dx squared is equal to this expression here. So here we're just applying our dt and dx relation here and just substituting them directly into our derivative terms. So I'm going to do that, and I'm just going to substitute them in. And what we wind up with is this expression here, where I basically left this term alone, and we have an e to the theta here. Okay, and then we can start collecting basically everything here has an RU T naught squared over R naught squared EA, and we see we have the exact same thing on this term over here. Then simplifying, I'm going to divide both sides by this RU T naught squared over R naught squared EA, and when I do that, we wind up with this. Oh, and I'm going to divide by lambda too. I wind up with, I divide by this, and we wind up with a really sort of crazy constant here. And I'm just going to call this delta for the sake of having to write it 10,000 times. And it also looks intimidating. So if you take this giant constant here and just call it something else, it sort of hides the fact that it is a constant, but it sort of emphasizes the fact that it is a constant, and sort of hides the fact that it's a really complicated constant. Okay, and so using our delta and theta, we can show that our governing ODE, our boundary value problem, simplifies to this equation here in dimensionless form. And so again, basically delta, kappa are both constants. Okay, and so this equation, at least to me, looks a whole lot less intimidating to solve than this equation right here. Okay, and so, and in fact, when I was researching this stuff, this is actually an equation. It's called the Louisville Gratu-Gelfand equation, and it comes up in astrophysical applications and a few other places too. And so there are solutions to this equation here. I'm not going to go over them because to me they are very non-obvious. Okay, and then there are also boundary conditions that we have. We just basically apply the boundary conditions that we had before, and then basically non-dimensionalize them, and we wind up with d theta dz at the center of our material. It has to be 0 due to a symmetry condition, and we know that the temperature at on the outer edge is equal to T naught. Well, if we look at theta and plug in T naught, theta will be 0 if T is equal to T naught. And so that's a fairly nice boundary condition to work with. So theta, and also Z is equal to 1 at X is equal to R. Because again, this outer radius here is R naught, and X is pointing from the center. Okay, so we have our boundary conditions, and we have our equation, and you can solve this should you want. And we are looking for the steady solution, and I'm going to work on the planar case, which is kappa is equal to 0. Actually, in this case, the cylindrical version with kappa equal to 1 is actually easier to solve than the kappa equal to 0 case. I've never solved the kappa equal to 0 case, so if anybody knows how to do that, I would be curious to know. But to me, it is completely non-obvious as to how to actually show that if you solve it, you can develop a relation between delta and theta m, and theta m is the max theta in the system, which is at the center. Okay, and so you can show this expression here, where basically delta, our constant, is equal to twice e to the minus of the maximum value of theta times arc cosh of e to the theta max over 2. That's a really bad 2 over 2, and that quantity squared. So to me, crazy non-obvious. But if you plot it and you plot delta, or you plot the maximum value of theta as a function of delta, you wind up with this curve here. And so as we increase delta, and by increasing delta, recall that delta essentially has this heating term in it. It's a dimensionless heating term versus the heat loss term is basically what it is. And basically, if you bump up delta, you sort of bump up the heating rate. And so so again, if we have no heating, you basically start here, and you would expect you'd expect if you have no heating, then theta is unchanged everywhere, and so theta max will be 0, which is what you would expect. Then, as you increase the amount of heating, you expect more and more and more. You expect more and more and more a larger and larger and larger increase in temperature, i.e., theta in the system, as you go to the right and increase the amount of chemical heating, or increase the ratio of chemical heating to the heat loss to the system. And so you start to creep up, and eventually the nonlinearity in the solution and the Arrhenius term kicks in, and you start to go over this bend here. And above this point here, basically, if you increase theta further, if you increase delta further, there is no longer a stable solution. And so And so from this point to the right, there is no longer a steady solution. So in other words, our ignition criterion is if delta is greater than, if delta for our system is greater than the critical delta, we will thermally explode. And just, this is, the solution to the system is similar to Semenov, and that there are basically two branches. If there is a steady solution, there are two branches. This here is the stable branch. This here is a mathematically unstable branch. And so even though this is technically part of, this is technically a second possible solution, it is mathematically unstable, and it is analogous to, it is analogous to the unstable temperature node for the Semenov analysis. Okay, so are there any questions with this?
Just had a question about the T minus T naught being small assumption. So is that basically the temperature at which we start to seeing any reaction? Is that why?
More or less, yeah. I wouldn't say any. I wouldn't say any reaction, but it's the temperature where we start to see it's the temperature where we start to see the reaction starting to overwhelm the rate at which it can be lost through the outer walls, and that just happens if you put in the parameters for an energetic material and use reasonable conditions. It tends to be, you know, a 10-20 degree change in temperature.
Gotcha. Okay, so that's not assuming that you're able to dump heat to your environment then?
Yeah.
Okay.
Yeah.
Okay, gotcha.
Yeah. So when he's doing this analysis, they are interested in finding an initial temperature of the energetic that's going to start to cause problems. And so they are already elevating the temperature up. So for instance, you wouldn't want to start this at, say, 300 Kelvin, and then basically say, well, the change of temperature, it needs to be 200 Kelvin to get it to ignite. That would start to violate some of the assumptions in this analysis. And so basically he's asking the question, what kind of temperature do I need to get this to start to react rapidly? You know, is it going to detonate just sitting there in a munitions bunker by itself, just minding its own business, or, you know, or does it have to be subjected to some sort of fire? You know, or aircraft are hot. Is the temperature inside of the aircraft, is that going to be enough to get it to light up? You know, these are the kinds of elevated temperatures that he was asking. Okay, any other questions? Okay, and you can show that delta crit, which is just this peak here, is equal to 0.8785 for planar slab. Again, this is planar slab. And the maximum value of theta is 1.1868, which is a fairly small, modest, basically 20%, you know, a fairly small, modest increase in temperature. And qualitatively, for both the cylindrical and spherical coordinates, you see a qualitatively similar curve. Okay. And you can repeat this process where you basically solve the radial version of this approximate Frank-Kamenetsky equation, and then you build a relationship between delta and the maximum value of theta, which is at the center of the sphere or the center of the cylinder, and then you plot theta as a function of delta, and find the maximum delta, and then that is your explosion criterion. Okay. Yeah, because again, if you increase the basically ratio of the chemical heating to heat loss further, the chemical reaction starts to overwhelm everything and the system explodes. Essentially what happens in the governing equations is that basically these terms here start to dominate and basically overwhelm basically these terms here, to where the chemical heating term, it is impossible for this heat conduction loss on the left hand side to be balanced with the total heat generation produced by burning on the right hand side. So it is impossible for these to be balanced if delta is greater than delta crit. Okay, and so that's that. And then you can repeat this for other geometries, and you can make a little table. Here is that basically for a slab, which we just did, a delta crit is 0.88. For a cylinder, it's 2. For a sphere, it's 3. If you do a cube, it's 2.47. If you do a regular cylinder, it's 2.79. I don't know what a regular cylinder is. I don't know what the aspect ratio is. And if you do a brick, again, I don't know what the aspect ratio of the brick is. You find that it's 2.94. And so it's interesting to note that of the geometries, the slab is the one that has the smallest delta crit, and that makes sense. And the sphere is the highest. And so, and then that makes sense because the slab has the worst surface area to volume ratio. That is, you could think of that the amount of heat generated inside of the slab scales with the volume, and the amount of heat loss scales with the surface area. And so the slab has this worst ratio in terms of ignition, whereas the sphere has the best surface area to volume ratio. Okay, and so you would expect that due to the increase of surface area for a sphere, that you would need to heat it up quite a bit more to get it to ignite. And then that intuition is sort of born out of this Frank Kamenetsky analysis. And so if we have our system and we have our energetic material, it's at temperature, it's at some temperature T naught, and it has some size that we're designing for, and we calculate our, and we find some chemical reaction parameters, and we calculate our delta. If our delta is greater than the values in this table, we really need to worry about a thermal explosion. So now the question is how do we use delta crit? Again, as I said before, that for a given design, you could say R naught, lambda, A, EA, etc. We actually want to know what the largest T naught is that does not cause an explosion for a given material. Okay, and so what we can do then is solve we can solve a delta crit, and I'm going to call this temperature where it starts to explode TC T crit. And we can basically just solve this expression here for the temperature which will cause it to explode. Okay, and so in doing this, we basically wind up with the critical temperature is equal to the activation temperature over the natural log of this crazy argument here. And note this, the natural log of this crazy argument here also depends on the critical temperature. So this isn't a nice algebraic equation that you can just punch a number into your calculator. Is that you need to actually solve this equation here if you want to find the critical temperature. However, this one's pretty easy to work with. Is that because to find T crit, to find the critical temperature, you need to know the critical temperature. And so this equation here is very easily solved by just iterating on it using what's called fixed point iteration. Where you basically guess the value of the critical temperature, stuff it into the, basically stuff it into this natural log term here, and then that gives you a new critical temperature. Then you take this new critical temperature and put it back into the log. Then you keep going around in circles like that, and usually 4 or 5 times this expression here will converge very, very rapidly. Okay, and so if you have a given diameter and chemical and then other design parameters for your system, you can estimate at what temperature can I subject this energetic material to before I need to worry about it blowing up on me. And then if you plot the solution to this, we can find that for a sphere, is that the smaller the sphere, the higher the critical temperature is, and the larger the sphere, the lower the critical temperature is. Okay, and so basically, why is that? Well, if the sphere is super small, that basically our AS over V is extremely, for a small sphere, is extremely high. And so basically these systems here tend to lose a lot more heat than they gain by chemical reaction. So you need to heat it to a much, much larger temperature to get it to start to explode. Whereas if it's large, you have a small AS over V. So you have a much larger volume relative to the surface area, and because of that, the sort of chemical, it is much easier for the heat generation due to chemical reaction to overwhelm the heat loss from the surface. And so as we increase the diameter of our energetic material, it is actually easier to ignite, which at first when you're getting used to this, that actually seems counterintuitive, because you would expect the small one to be easy to ignite relative to the small one to be easy to ignite relative to the larger one, but in fact, the opposite is true. And then that's also born out of experiments. Okay, so are there any questions on this?
And so was this only for the steady state version of this? So this doesn't take into account non-steady or the time it takes for heating to reach the center of the sphere?
Yeah, this is for the steady solution only.
Okay.
Yep, but if you want some confidence about this, about how well this works, is that there's a table in Cooper's book where he compares the for various explosive charges, he compares the calculated critical temperature based on Frank Kamenetsky analysis to experimental values. And notice, like, let's look here at RDX. It was calculated to be 217 degrees Celsius, and experimentally for the sample thicknesses that they had, it was 214. For TATB, which is an insensitive explosive, it was 334, and they measured that to be 353, which again is fairly close considering all the crude assumptions that Frank Kamenetsky had to make. And you can see that for a lot of these explosive materials, HMX, etc., these are all very close, basically very close. So despite the fact that it's a steady solution, despite the fact he linearized the crap out of, or he greatly simplified the chemical source term He ignored any of the changing density that occurs with the chemical reaction. He assumed constant temperature. He ignored any of the real processes that occurs. He even ignored oxidizer depletion. Yet, even with those crude assumptions, he still gets very decent results. In fact, just looking at this table, about the worst one that I can look at would either be TATB or BTF, and I don't know what BTF is off the top of my head. Okay, and so those would be the worst, but all the others are actually pretty good, and I don't know why those two are so bad compared to the others, but all the others are essentially spot on. And so, despite the crudeness of this theory, it appears to work. It appears to work very, very well, at least as a back of the envelope type of scenario. And so I just had a little note here on what does a transient solution look like, which was sort of brought up earlier. And that's what you guys will be analyzing for your homework. And so if we start with a flat temperature profile here, and basically the heat generation, there will be more heat loss. The rate of heat loss will be higher near the walls than it is at the center. So the center starts to spike up. Then if the temperature spikes up, then the center will basically burn more rapidly. If it burns more rapidly, then the center line increases, the temperature of the center line increases further and further and further until the center is at a high enough temperature to start to run away. And so you start to form a spike at the center at the center line temperature as it starts to thermally explode. But due to heat conduction, the very rest of the material is not at a high enough temperature to ignite yet. So you basically wind up with this huge temperature gradient. And then there'll be a reaction wave that will propagate from the center towards the outside. And you could kind of argue that that reaction wave is similar to, or at least for this type of model, is similar to a flame. But again, if you were to that is related to part 3 of that problem. If you were to calculate, basically use the results and basically calculate how fast this wave is propagating, it will be propagating at about half the speed of light, which makes no sense. And that's due to a lot of inherent assumptions that are in the Frank-Kamenetsky analysis that are completely incorrect. And so that's just sort of how it goes. So the Frank-Kamenetsky analysis is basically valid up to this point here, where the system is starting to run away. After it has run away, the Frank-Kamenetsky equation will produce pretty pictures, but they are completely physically incorrect. Okay, because other processes will take over that will basically limit how fast the combustion wave propagates. It will not be propagating at the speed of light. It will or faster than the speed of light. It will be propagating at much more realistic speeds if we consider additional effects. But nonetheless, this Frank-Kamenetsky is really good for basically analyzing, performing a pretty simple analysis to find an ignition criterion. So are there any questions?
So you can use this for giving us, like, say, constant heat flux from the outside. You could look at the time at which it would take to reach that critical temperature.
Yeah, you could look at the time and also where it ignites. Because if you heat it from the outside, it may ignite. You know, there are if you're heating it from the outside, you could depending on various parameters, and it can ignite in a couple of places. One, if you're applying a high heat flux here, you can actually heat it up so fast that it ignites on the outside. And that is analogous to taking your energetic material, a slab of it, taking a torch and just heating the outside of it very rapidly. That is what you want to do if you want to start if you want to start what's called a deflagration, a wave going through the energetic material, is you want to heat the surface extremely rapidly. If the heating rate is a bit slower, what happens is that the ignition will not occur right on the outside, and you'll have some sort of reaction wave coming in. What will happen is there will be some internal heating, and it'll ignite basically slightly, will ignite slightly to the inside if the heating rate is slower. And this condition here is extremely dangerous because if you start to heat it and it ignites from somewhere in the middle, it's an extremely dangerous scenario. And when we discuss explosion theory towards the end of this class, you will understand of basically how these temperature gradients that are formed just before it ignites, if they're internal to your system, are extremely dangerous. Okay. And this process here that you talked about is actually called cook-off. I mentioned this earlier. And the DoD and DOE are still extremely interested in cook-off, but it is extremely complicated to model. And you could consider cook-off as a very physically consistent and correct version of modeling Frank Kamenetsky, where the litany of assumptions that I made in deriving this, you get rid of all of those. And what makes cook-off really, really complicated is not only do you have to consider the heat equation and depletion of chemical reactions, and you need to consider multiple chemical reactions and realistic chemical reactions, etc. But you also need to consider the solid mechanics, all the fracturing of the crystals and things like that to basically modeling cook-off. And so we will not be modeling cook-off in this class anytime soon. But if you have any good ideas on modeling cook-off, there will probably be some funding for you in your career down the road. Hey, are there any questions on this?
Professor, just a real quick question. Even this transient solution is still only valid for before the explosion, correct?
Yeah, so basically after the temperature starts to spike up, it is no longer valid.
Okay.
Yeah,
So,
go ahead.
oh, so when it spikes up, that's when you know it explodes?
Yep.
Okay.
Yeah, and so one way that you can tell it explodes in your code is if you plot theta m as a function of time, which I think I kind of asked you to do, is essentially I asked you in one of the problems to essentially basically make to basically remake this curve here, and then basically what you'll find is that your computed curve, the actual or the theoretical curve will look something like this, and the computed curve will wind up looking, it'll be almost exact up to a point, and at this starting at about here, it'll start to deviate a tiny bit, and that's just due to his assumption on linearizing the 1 over t, and then it'll go up to here, and then it'll it'll go up to here, and then it'll just shoot up. And here, this will shoot up to about, the temperature will be about 10 to the 19 Kelvin. But what is interesting is that the critical point, if you use in the analysis that basically you are doing, will be very close to delta critical that is done by approximating the Arrhenius term. Okay, and so yes, and so basically, if you plot theta max, you can consider it ignited when you start seeing temperatures of 10 to the 19 Kelvin. And the code will be stable at that point. That is not numerical blowing up nonsense. That is an actual third stable point. Okay, does that make sense?
Yes, yes. Thank you.
Yep. Any other questions? Okay, I guess this is a good enough place to stop. It's not worth starting detonation theory in the last 5 minutes of class. So are there any questions with the homework?
Yeah, I have a question on the first problem. I'm just trying to understand the interfacial boundary that we're setting up for that problem.
Mhm.
So for a fuel, we have a fuel that's evaporating into air.
Yep.
And because the evaporation is diffusion driven, that within our control volume there, basically it's completely saturated with fuel. And so fuel has to then leave that control volume for any more fuel to continue to evaporate, right?
Exactly.
So then is there diffusion of air into the fuel at all? Or can we assume that air does not diffuse into the liquid interface?
Yeah, you can assume it doesn't go into the interface itself, but remember, you'd have some sort of omega dot I leaving the surface, correct?
Yeah.
Okay, and basically that's kind of what you have to find. And then you'd have a bulk flow out of that species and rho yi vi. And note that so that intuitively, if you are generating vapor, you're going to have a non-zero diffusion velocity, right?
Right.
So for the other species air, remember there's the condition that there can be no bulk flow induced by species mass diffusion. So that means that the sum of rho yi vi is equal to 0, even at the top of this control volume. Is that basically this fundamental condition still holds. So this implies that V of air, say, is not equal to 0 if V of fuel is not equal to 0. Okay, so that means that there is also there's also air diffusing towards the surface, or there are other species diffusing towards the surface if there is mass diffusing away, and that's just sort of it's sort of counterintuitive and kind of confusing at first, but after you work with it, you'll start to get used to that. This is very much von Neumann has a famous quote where he said something along the lines of when he's talking about his detonation theory and just high level physics in general, is that you sometimes never really understand it, but you eventually get used to it. And so this would be one of those cases where after you work with it, you start to get used to it. Does that help? I hope it does.
Yeah, I think that helps. So we don't really need to consider our control volume into the fuel at all. And consider diffusion of the fuel into
Well,
the
yeah,
fuel?
you can, but what is the mass fraction of air inside of the fuel?
0, right?
What is the mass fraction of gaseous fuel on the liquid side of the fuel?
I guess 0.
Yep, exactly.
Okay, so yeah, there's really no, that's what I was confused if, so for a subcritical liquid, that by definition means that it's completely a liquid. There are no vapor fractions in there, right?
Yeah, I mean, you can make it complicated where you have a bubbly interface where you have a bunch of little bubbles inside. And when we do propellant combustion, we will worry about that. But for now, just treat it as a pure fuel that there's nothing else that you're not dissolving any air into the liquid or anything like that.
Okay.
Okay, but in reality, you do have to worry about air dissolving into the surface and things like that. I mean, for combustion, that stuff usually is not important. But in the general case, you do need to worry about air dissolving into the surface and and other solubility things. And also to your point, you mentioned subcritical. If it's supercritical, you have no interface, and this analysis is not needed.
Because it's at that point it's gas.
Well, it's not gas. There's just
Or
there's no gas liquid interface. Remember, a supercritical fluid they tend to have the density of a liquid, but they have the thermal physical properties more of that of a gas. So they have the viscosity of a gas, and the surface tension is 0 because you have no interface. And so the absence of an interface between the liquid and the gas really sort of changes things. And towards the end, I'll review a couple of papers where basically they discuss supercritical droplet vaporization, which would be important for those of you who want to go work with, if you want to work with rockets. You might be concerned about that. And so you will just show how that's different than normal droplet vaporization. Okay. Any other questions?
Thank you.
Okay. Well, thanks, guys. We will see you on Wednesday.
All right. Thank you.